I'd like to continue my Introduction to Nomenclature video series with the nomenclature of stereoisomers. We'll begin with the Cahn-Ingold-Prelog rules. Stereoisomers are compounds that have the same order of atom connectivity or bonding, but they differ from each other in 3 dimensions. For instance, this is the structure of 2-butanol. The compound on the left has an OH going back into the screen and an H coming forward on C2. By comparison, the molecule on the right has an OH coming forward and an H going back. These two molecules are not the same, and it might be helpful to build a model of each of them and then try to superimpose the models to convince yourself that they indeed are different. Another example of stereoisomers are the 2-butene isomers. The compound on the left has methyl groups that are across from each other, or trans on the alkene, while the molecule on the right has the methyl groups on the same side of the double bond. Since you cannot rotate around a pi bond without breaking the pi bond, these two molecules are not the same either. To learn to name stereoisomers, you must learn and apply the Cahn-Ingold-Prelog rules for nomenclature. So let's start by looking at some sp3 hybridized carbons that are bonded to an asymmetric carbon atom. In other words, there's no symmetry on the carbon atom. The first rule is to look at the 4 groups that are bonded to the asymmetric carbon and assign them priorities, with the higher atomic numbers receiving the highest priority. So in this example, we're comparing fluorine to carbon to hydrogen to nitrogen. The highest atomic number atom of those 4 is the fluorine, so it's assigned the highest priority, or number 1. Nitrogen is next, number 2. Then the carbon is number 3. And the hydrogen is number 4. If you have a molecule that contains isotopes of the same atom, such as carbon-12 and carbon-13, or hydrogen-1 and hydrogen-2, then the heavier isotopes have the higher priority. So in this example, carbon-13 would be the highest priority, carbon-12 would be second, H2 is a deuterium atom, would be third, and the protium atom, H, would be number 4. So let's look at a little bit more complicated example. If there is a tie in the first atom, then you have to move along the chain one atom at a time until a difference is found. For the stereocenter that's shown here, I'm comparing carbon, hydrogen, carbon, and carbon. The 3 carbon atoms are tied in terms of atomic mass, so we have to look a little further. Looking at the ethyl group that's on top, I have a carbon that is bonded to a carbon and 2 hydrogens, and so I've written that here. Looking at the bromoethane group, you see that the carbon here is bonded to a carbon and 2 hydrogens as well, so we're still tied with those 2 groups. And the third carbon is bonded to 2 carbons and a hydrogen. So what I know at this point is my highest priority group is the one that is carbon-carbon. These 2 are tied, and my lowest priority group is the hydrogen. So we'll need to continue marching down that chain until we find a point of difference. So clearing up the screen a little bit, priority group 1 is the isopropyl, priority group 4 is the hydrogen, and so we go on down the chain and compare the methyl to the CH2Br. The methyl is a carbon bonded to 3 hydrogens, and the other carbon is a carbon bonded to a bromine and 2 hydrogens. The bromine is a higher priority than the hydrogen, so this will be priority 2, and this will be priority 3. If there are multiple bonds present, each multiple bond has to be treated as an additional single bond to each atom. So let's take a look at an example. In the molecule shown, I have an aldehyde, a nitrile, and an alkene that have multiple bonds present. If I very clearly show those multiple bonds, the structure would look like the one on the screen now. What we're going to do for the purposes of nomenclature only is we're going to get rid of one of the pi bonds and make it a single bond on each atom. So I've added a new CO bond to the carbon and a new OC bond to the oxygen. Same thing with the triple bond. I'm going to have 2 additional single bonds to the carbon, 2 additional single bonds to the nitrogen. Same with the alkene. Let's clean that structure up a little bit. So now let's look at the 4 substituents bonded to the stereocenter in the center of that molecule and the atoms that are attached to them. All 4 are carbon atoms, and so I'm tied at this point and I need to march out the chain a little bit. The carbon on the top is bonded to 2 oxygens and a hydrogen. The carbon on the right is bonded to 3 nitrogens. The carbon on the bottom center is bonded to 2 carbons and a hydrogen. And the carbon on the left is bonded to 2 carbons and a hydrogen. So what I can tell so far is that the aldehyde is going to have the highest priority and the nitrile is going to be second because I'm comparing the oxygen to the nitrogen. The oxygen is higher to a carbon and a carbon. Cleaning up the structure a little bit, I now need to figure out which is priority 3 and which is 4. For the isopropyl group, I have a carbon in the methyl that's bonded to 3 H's. And for the alkene, I have a carbon that is bonded to a carbon and 2 H's. A CH is lower in priority than a CC. So looking at this, I'm going to have my 3rd priority group is the alkene, and my lowest priority group is the isopropyl. So looking at a summary of the Cahn-Ingold-Prelog rules, first you would assign priorities by atomic number. The higher the atomic number, the higher the assigned priority. And then when you're comparing isotopes, the heavier isotope is assigned the higher priority. If you have a tie, you need to move down the bonds until a difference is found. And you also need to split up pi bonds into single bonds to each atom. I'll discuss what to do with these priorities in a separate video. Let's give a few examples a try. I encourage you to rank the priorities of the groups attached to the stereocenters in these 2 molecules. Pause the video, write out your answer, and then take a look at the next screen. Okay, time to look at the solutions. For the molecule on the left, I'm simply comparing a chlorine to a hydrogen to a deuterium to a carbon. Chlorine is highest, carbon is second, deuterium is third, hydrogen is fourth. The second structure is not as obvious. One thing that I want to do is clearly show the bonding in the aldehyde and break that pi bond that was originally between the carbon and the oxygen and show it instead as an extra bond between the carbon and the oxygen and an extra bond between the oxygen and the carbon. So let's take a look at the rules. Carbon, 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 carbon. I'm all tied. Taking a look at what's bonded to the aldehyde, I have a carbon with 2 oxygens and a hydrogen. Looking at the CH2, I have a carbon bonded to a C and 2 H's. Looking at this one, I have a carbon bonded to 2 oxygens and a hydrogen. And here I have a carbon bonded to an oxygen and 2 hydrogens. So what I know so far is that the CC is the lowest priority group. I'll give that one a 4. I know that C bonded to O and H is lower than priority than C bonded to OO, C bonded to OO. So this is group number 3. Let's clean up the slide a bit. Now I need to compare the aldehyde to the acetal. The aldehyde, the next atom out, is an oxygen, and it's bonded to 1 carbon. For the acetal, maybe it would be helpful to write that out. So there's my bond to the carbon, and it's got 2 OCH3s. If I take a look at one of those oxygens, I see an O bonded to a carbon. I'm still tied. For the aldehyde, I'm out of atoms. But for the acetal, I have another oxygen, which means this is going to be a higher priority group, and this is going to be a lower priority group. So here is our final priority assignment. I did use Wade and McMurray as references when preparing this video.